To CBL Science for Citizens lectures for spring 2020. My name is Thomas Miller and I have the honor and privilege of being 6th director at CBL and the host for these Science for Citizens lectures. The goal in these lectures is to bring our very best science to the community so that people in the community can understand what we do and why it's important. As a rule, these lectures are held in person in one of our lecture halls here in Solomons, and 3 very generous companies, PNC Bank, Southern Maryland, Toyota, and Team Hyundai, pay for refreshments and cookies for those who come to hear the lectures. Obviously, we haven't worked out yet how to get tea and cookies to all of you in your homes, but those 3 companies generously continue to support our programs while we're doing them virtually. So we thank them for supporting our work and for supporting the environment. This evening, we're going to present a lecture from one of our environmental chemists. If you have questions during the course of Dr. Gonsior's presentation, please type your question into the chat box, and I will moderate questions at the very end to try and bring together questions into groups and themes and challenge Michael on some of his ideas and concepts. So tonight it is my very great pleasure to introduce one of our CBL faculty, Dr. Michael Gonsior, who's going to talk about what's in our water. Michael hails originally from Germany, where he conducted his undergraduate and early graduate work, but it's apparent from looking at his resume that he had a wanderlust from a fairly early age. He did his PhD in New Zealand. He then went to the University of California, Irvine, to do postdoctoral work. In between that time, he has spent time volunteering for Engineers Without Borders, developing water systems in Africa and South America. He did a second postdoctoral appointment at a university in Sweden, and he interviewed for the position he now holds while on a research boat in the middle of the Sargasso Sea, if I seem to remember, Michael. That wanderlust continues because he will be leaving us for a year's sabbatical at the end of this summer and going to the University of Montana, where I understand the fly fishing is very good and the opportunities for collaboration and chemistry are also very good. So it is my absolute pleasure to introduce tonight's speaker, Dr. Michael Gonsior. Michael.
Thanks a lot for that kind introduction, Tom. And you're all here, so you were not scared away by the word chemical in the title. So I'm hoping you'll still be here in 40 minutes or so from now, talk about a few things we do here, but it's also quite an overview. So I'm switching now screens.
Yep.
So that is,
and then this one.
The presentation. Bear with me a second here. All right. All right. So the title, What's in Our Water? A Chemical Perspective of the Good, the Bad, and the Ugly. My wife can tell you that I'm not necessarily a big fan of Western, but that title is really appropriate to talk about some of the things we might find on the chemical perspective in the water. And I want to talk about these in pretty broad terms, because you can imagine that you can spend a lifetime of research on either one of those parts in the water. So let's get started.
Sorry, use the down arrow key.
So it's not there. Sorry for that. So So we're going to talk about water and the chemistry within, but we're not talking about what we call inorganics. So you might be more familiar with the term nutrients. So this is not a talk about nitrogen. It's not a talk about phosphorus. It's a talk about all other kind of organics. And the organics is not meant to be here as a term that it's good for you or healthy when you go to your organic store. It's a term which is actually defining organic chemistry. It's just the chemistry of carbon, hydrogen, oxygen, sulfur, and all those chemicals you can make with us. So let's see. If you remember the movie, you see those characters, the good, the bad, and the ugly. So we're gonna go to a little riddle at the beginning because I want to understand one specific compound, which is of utmost importance here. So, which is one name of it is actually dihydrogen monoxide. So this is already, so hopefully not some people already left because I mentioned a chemical here. But what do we know about this substance, dihydrogen monoxide? You might know what it is, but I want to talk you through because it's incredibly important to understand some of its properties, because this chemical is actually known to be the best solvent known to chemists. It's absolutely incredible what you can dissolve in it. And this talk is about a lot of those chemicals which dissolve in it. So it is corrosive, at least for some metals. It has unique density anomaly, which is very unusual in chemicals. It's also highly hypertonic and cause death in humans when you actually consume a lot of it in pure form. So if you remember chemistry from high school, you might now know what that is, right? It's oxygen, 2 hydrogen, and this is it, H2O, water. So water is incredibly important because otherwise no life on Earth would exist. But it's not pure when we find it on our Earth's surface. So I want to talk to you about what's in it. And to do that, we need to talk a little bit about the water cycle. And then we'll talk about what dissolves in that water. So here we go. That's the water cycle. When water precipitates down in rain, snow, and so forth, when it melts from the mountains, it flows down and is evaporated again. You all know it. But one important part is there's a lot of organic matter coming into the water. And this is mostly from plants and all degrading organic material you can think of. If you're composting in your garden, you're making compost, but you actually, when you put water in, you will leach out some of those organics. And they're important because they are really going everywhere. The interesting part about it is that it's incredibly complex. You would not believe how diverse those chemicals which are in the water. We still don't know much about them because it's so complex. Over 80% of everything which is in the water, we just don't know what it is. It's intriguing to actually research this for an understanding what it is and how reactive it is. Because it's also not that you go to one spot and the other spot that it's the same organic material, because it's what we call dynamic. It's changing over time. So, but of course, we're not living in a pristine Earth. We're living on a planet which is heavily impacted by us. So the water cycle also changed quite a bit. And we call it, in this case, the urban water cycle. The water itself is influenced by other things now than just pure water and organic matter, which comes from plants and then degrading organic matter naturally. So here you can see the depiction of some of what we do. Especially, I want to highlight a few things here. That's the natural organic matter. We'll talk about a little. That's the good. We can talk about some acronyms here, which are going to go up or pop up. Pun intended here. These are persistent organic pollutants. That means they are around in the environment for a long time. So we need to talk about them because they do end up in the water. And then we can also put some other chemicals in the context. And these are what we call PPCPs, or pharmaceuticals or personal care products. So you will see those coming up later on in the talk again. So you see there's a lot of chemicals now which we make, which we use, which we discard of, which ends up in the water. So, but we also do something else when we make drinking water. We actually unintentionally make chemicals. And interestingly enough, we make unintentional chemicals directly before we ingest them. And this is done when we disinfect drinking water. We're making so-called disinfection byproduct. That means they're only existing because we disinfect the water. But we have to disinfect the water because otherwise the water wouldn't be safe to drink, because you have bacteria and pathogens and things that could kill you more directly, if I want to say that way, than the disinfection byproducts. So it is important that we try to control these and to understand them better. So that's also one research going on at CBR in my lab. All right, let's talk about the good first. When natural organic matter is produced, it is a product of the degradation of, for example, trees. Trees, of course, they're not soluble in water, but for example, fungi, they degrade that material and they make it water soluble at part. That's when that whole tree rots away and goes away. Some of it, of course, is what we call mineralized, makes CO2, but then other material is just leached out. If you take a little bit of your leaves from the backyard, put it in water, you see the color will turn a little brown. It's kind of making your yard tea. Same concept like making actual tea, because you're leaching out organics from your tea leaves. And here it's supported by organisms like fungi and bacteria. You see it in the color. So often that material has a specific color. You probably know your favorite fishing stream. Tom alluded to that. It might be brown in color or tea colored. These are organics. These are actually light absorbing chemicals, but naturally. But what I wanted to say here is that there is a staggering diversity of organic matter molecules in the water we drink every day, or we have been drinking throughout the evolution of life. So that means it's a good thing. It actually is not harmful. By the way, when you drink brown water and there would be no bacteria in it, it's actually probably, I would argue, good for you rather than bad for you, because there's a lot of chemicals in there which are probably antioxidants. So there's interesting. So if you go to a pristine stream in New Zealand, you drink the water, you actually can taste it, that it's sweet. These are a lot of sugars as well. So there's a lot in the water. And so what do we know about this natural dissolved organic matter? Well, not a lot. We know it's incredibly complex because we have new tools. We can look at the complexity as a whole, not necessarily to know what it is, but to know that it's there. Then we also know it's highly dynamic, it's reacting. So it's never the same, basically. Even if you take a sample, putting it in the sunlight, it will change over time to make different chemicals. And that's important when we talk about contaminants from us, because they're also changing to other things in the natural environment. All right, so to mention sunlight, in fact, if you're keen on a long-term experiment with a kid, take your bog water, which is nicely brown colored, put it on your roof or somewhere safe in the sun, and wait a few weeks, and you will see the color will change. It will get lighter and lighter until that color is gone. So if you have a lake and completely shut off the streams going in there, and it's really dark color, eventually it will be clear. The reason for that is what we call bleaching of this material by sunlight. Sunlight is energetic, puts energy in it, breaks up those molecules. Okay, it's also is interestingly enough, when we sample it, it's mostly pretty resistant to bacteria. You would think that material is fueling bacteria and things like that, but it's naturally coming out of the forest. The bacteria basically munched on it already for quite some time. So at the time you're actually seeing it in a stream or lake, it's reasonably resistant to further degradation. However, it does cause dramatic problems when we make the drinking water, and that is because nobody wants to drink brown water. So we're trying to take that color out, and that is not very effective. You have problems to take all of it out. And then what was left over, we call it their precursors to make other chemicals when we disinfect it. And unfortunately, we disinfect with chlorine. And when I mention organochlorines, that might ring a bell because some of the best known toxins, environmental problematic chemicals are actually organochlorines, dioxins you may have heard of, or other chemicals which contain chlorine. So this kind of things we're not making dioxin, but we're making chlorine containing compounds. So here's not to scare you off with analytical spectra here, but in analogy to the forest, you see that big hump there. There's a lot of signals. But if you really zoom in, you start to see the trees. And each tree you see in that spectrum, what we call it, represents a specific organic chemical. So you see that even in one sample here, you see thousands, if not tens of thousands of signatures, which represent individual molecules. So it's just an example to show you that it's actually extremely complex. And by the way, your drinking water wouldn't look much different than this. There's still tens of thousands, or let's say maybe 12, 15,000 compounds we can measure, but that doesn't mean we see everything. All right, so however, not all natural occurring chemicals are actually good. So that's, I call the bad, and coming now to natural toxins and engineering byproducts. So I mingle them together because they are bad, but they're not as ugly. And I'll come to the last part of the ugly one pretty soon. So the bad natural toxins, we have faculty within UMCs, specifically L place at IMET, at the Institute of Marine Environmental Technology in Baltimore, who works with harmful algal blooms. So there are algae that produce toxins, and what I'm saying by that, extremely toxic chemicals. But in generally speaking, the most toxic chemicals we know are actually compounds made by organisms or bacteria or algae. Botulinous toxins might be a term. Just unbelievable toxic this material. So most toxic compound, as far as I know, and that is something because I do know some chemicals which are pretty toxic. But what I really want to home in is a little bit more on the harmful algal blooms, because it's an increasing big problem. And I mentioned this because it also interferes with our engineering in drinking water production, because recent harmful algal blooms have created a lot of problems. Let's talk a little bit about quickly engineering byproducts. What do I mean by this? In this specific context, I mean chemicals which are produced in a way that they're produced by accident. For example, the famous example of polyfluorinated benzodioxins, or better known in the topic as dioxins, are produced by incomplete combustion of chlorine-containing organics. Like if you would burn your PVC pipe on your barbecue and put the lid on, that's probably not that you should do that, but it would make a lot of potential dioxins right there. So, but also what I mentioned earlier, those disinfection byproducts, they're a hot topic actually, because we still don't know them very well. So I'll come back to that in a moment. Okay, so let's have a look at harmful algal blooms. This was a paper published a little earlier in the Presidium National Academy of Sciences. This is a depiction of that massive algal bloom in Lake Erie, which triggered the warnings for millions of customers in Toledo and surroundings. So it was caused by essentially one type of organisms, and it's a cyanobacterium. Cyanobacterium as an algae, which is called Microcystis aeruginosa. This specific organism is problematic because it thrives in nutrient-rich waters. It likes it warm. It needs a lot of sunlight because it does photosynthesize, but it produces a toxin, a very potent toxin too. It's called microcystin. You see the formula here if you really want to know it. It's a type of a peptide, if you wish, that has a lot of nitrogen in it. But what happened in 2011 and 2013 is that it actually broke through the drinking water. They couldn't cope with all that algal matter, which was suddenly so massive and would just get into the intakes of the drinking water plants. And it would go into the drinking water because they couldn't fully remove it. So the problem is, you would think, why don't they shut down the drinking water? That's a great idea, but you cannot do it. You cannot physically shut down a drinking water plant, because when you do that, you lose the positive pressure on the distribution system, and then the water can actually penetrate in, because they're not perfectly sealed most of the time. Some of the systems are old, and that is actually a danger to get even wastewater in there. So they will never ever shut down the drinking water distribution system. Because of that reason, it would make it worse. However, you now have to protect the people. So they had to go out in massive campaigns and to warn everybody to not drink the water, because it's potentially harmful. So this is how far I can go with toxins and harmful algal blooms. So you have some headlines here. Recently was interesting. I'm not sure if you followed the news, but there were 300 elephants killed in Botswana. And they traced it back to an actually harmful algal bloom which killed them. Yeah. And we have a lot of discussions about our ecosystem out of balance because of the eutrophication, what we call. There's far too much nutrients in the environment, which are actually food for those harmful algal blooms because they need that high nutrient waters. But also in terms of climate change, warming waters in general promote more of these blooms as well. So there's a lot of studies now supporting that hypothesis. We have a lot of news making events, unfortunately, about harmful algal bloom, to the point that we even have algae which also produce toxins which actually glow in the dark. And that was one here in the Chesapeake Bay. All right, so if you see something like that with your boat, you might consider not staying too long. So engineering byproducts, and that's really what I do a lot, looking at this disinfection byproducts. Or I should say we as a group, we have some funded projects to do that. Why is this important? So it was incredibly important to disinfect our waters because people were dying from drinking contaminated, bacteria-contaminated water all the time, and they still do in some parts of the world because they can't have access to clean water. So this was really probably the technology which saved the most lives. But we also created a side effect, and that's a complex slew of low concentration, but they're there, of disinfection byproducts. The first discovery is going back to 1972, when chloroform was discovered, and everybody freaked out. What? We're making chloroform in drinking water. And then shortly after, some of those chemicals were regulated. And we are at 12 regulated disinfection byproducts, and we know over 800. So this tells you a story that there's no catching up. And I would argue also that out of those 800, we only know 50% of the total organic halogens made in drinking water. I don't want to scare you, the water is pretty safe to drink. However, there is the remaining part which have low concentration of chemicals which are actually problematic, and so chronic exposure, that means you drink it every day at high chlorine dose, you might actually end up with some health effects which has traced back to actually even a liver cancer and miscarriage and so on. So here's another example. We had that as a forest. So the top is before disinfection, the bottom is after disinfection. What those blue circles really are, they show you those chemicals which were made, and just in that small little zoomed in area. So you can imagine if you then extrapolate to all of the entire spectrum, if you look through all this forest, you will find a lot of new weeds in there, which are those disinfection byproducts. And that's what we can look for, and that's what we are doing here to discover new disinfection byproducts. Not that we necessarily know exactly what they are on a structural basis, but we know they are there. And this is actually, in fact, an actual drinking water before and after disinfection. So if you think you're drinking really clean water, that's not quite the case. But it's also not a problem in a way, because we're used to it. We have been drinking not pure water through our entire evolution. Okay, so So now you're probably switching off the screen and go home, but these are just some chemicals, and this is not to go through these, but these are potentially made, and we hypothesize these through different mechanisms. Just want to show where that change happens on the molecule. So you see, it's a staggering amount, even on this small selection of compounds we're proposing in the structure of. So it is quite a remarkable problem, and it's probably still, I would almost argue, generations of scientists will work on that problem. One more thing about disinfection byproducts, and that is most people don't know it, but in wastewater treatment, before wastewater is discharged into a river or a lake or wherever, or the Chesapeake Bay, it has to be disinfected. The reason for that is they don't want to discharge any pathogens and any potentially problematic bacteria. So similar reasons why you disinfect drinking water. Here, the water doesn't go directly to your house, but it goes to a river or a stream and so forth, or the Chesapeake Bay. However, the composition of that, what we call precursor, or that organic matter within that, is fundamentally different to what it's in the stream in the first place, what comes from the degradation of trees and plants and other things. Here we have human waste, mostly, or chemical waste as well, which is processed to a high degree now. We have really advanced technology to treat the water to a pretty high level, but then we disinfect it. And there is very little research done on what these chemicals are, which are made then, which are very different material, which is getting chlorinated than before. And here we are, and it becomes important that now you have all this personal care products, your soaps, your shampoo, you name it, your washing powder. That's all organics in there, and now they can react with the chlorine and making some very unusual organic chlorines, which getting discharged into the waterways. I looked at this a little bit. We tried to get funding for this. We're still working on it. So it's an chemically intriguing problem to really get a little bit more handle on what these compounds are. Okay, so here are some structures again. Again, this is just things we found. So they are completely new. They've never been described. So these are all kind of, in a way, scary molecules because we have no idea what they do. They are breakdown products of actually detergents, but then they get chlorinated. So their toxicity is completely unknown. The environmental fate is completely unknown, and so on and so on. All right. So while we're there talking about the chlorination of personal care products and pharmaceuticals, I want to just jump right into that. What is this? So we're still talking about the bad here. So we're not even there with the ugly. So the personal care products actually are extremely diverse. You can imagine when you go to a supermarket or pharmacy and buy your needed drugs for whatever health reasons, that's already pretty amazing how many different chemicals you actually buy for a specific purpose. Of either it's painkiller or is your allergy medicine and so on, or your shampoo, your razor cream, and whatever. All of these have an incredible diversity of chemicals in them as well, and they do end up in water. So, in fact, that's one part, but they're not just staying in the water. They're changing. The bacteria, much of them, they might change it a little bit, or they just break apart in different regimes anyway. So, and then of course, if you then put a strong reactant like chlorine on it, they're making a whole slew of new chemicals. So the diversity is just, you can't handle them as an environmental chemist. So you can only look at indicative pathways, what's happening, to infer what might be going on. All right, of course, pharmaceuticals are designed in the first place to interfere with our body. So they're doing something. So now you can imagine when they go into the environment, they're doing something to other organisms as well. I mean, if you do it to mammals like humans, they're going to probably do it to other organisms as well, but not in the same way. So there's a lot of Endocrine disruptors are a big topic, which means they're actually interfering with the hormones in organisms, so they're changing it. It goes to changing in fish sexes, for example, that have been shown, but all kinds of interferences in the metabolism of organisms. So we talked about this very complex system. So and it's actually it's a massive scale. If you just look at that wastewater discharge, we're talking about billions of gallons of water in the US alone, which means this is impacted some way or the other by pharmaceuticals and personal care products, plus chemicals coming from the industry. So, and I mentioned that earlier, degradation transformation products remain largely unknown. So this is really a dilemma when we quantify a specific chemical because we know that it's toxic. So we want to know what impact it might have on the environment. That's a great thing to do, but we have no idea if it's a slightly modified molecule, what that does. And there is evidence that actually if you change it, it might make it more toxic as well. Here is a very busy slide, and you can look this up at the EPA website, actually. I just want to highlight a few things here about where personal care products and pharmaceuticals really come from. One, which is pretty close to home. We have a septic system where we live. You might have one where you live, because these things go into your septic and then it infiltrates into the ground. Yes, there might be some retention, but the water got to go somewhere. And if these chemicals are water soluble, and I told you that water is the best solvent there is, known to chemists, then you can imagine that a lot of those chemicals travel with that water, either into the groundwater or into your next stream. There is a lot of this material still going into from our wastewater treatment plants, even though the quantity is reduced dramatically. They're doing a fantastic job, to be honest, in removing these. There is still quite a lot in there. And of course, we have agricultural waste as well as highlighted here. And then on top, the circle shows you a little bit about the transformations. So now you're putting all those chemicals into the environment. Yeah, and then what happens with it? Fortunately, some may just not be around for very long. So that's what we call they're degrading quickly. They're mineralized, hopefully, to an extent that they end up being essentially CO2. But others get changed slightly, and then they're completely outside of what we can do as environmental chemists. So just we have no idea anymore what they are and what they do in the environment. So let's talk about the ugly now. There is a convention, the Stockholm Convention. They actually took on themselves to declare chemicals which are extremely problematic and persistent in this declaration. So they started with 12 chemicals. All of them are probably, you probably know them. So we're talking about famous contaminants which are around for a long time. But these are 16 new ones which was added a few years ago. And I want to highlight one component in here a little bit. And these are perfluorinated compounds. So if you follow the news, perfluorinated compounds or PFAS in general have made big news because they are also often portrayed in the media as the forever chemicals. We're going to talk about that in a moment. They're in this convention, they're there. And for completeness, I also want to give you the vision now, which are likely going to be added very, very soon. So these are now industrial chemicals most of the time. So there's dechlorine plus, which is flame retardant. Flame retardants in general have been a problem for a while, but that's a new one, which is extremely persistent. Methoxychloride is actually an organochlorine pesticide, which are also thinking about adding to the persistent organic pollutant list within the Stockholm Convention. And then one interesting part, and I did do quite a bit of marine debris or plastic work over the last 10 years. It's a UV filter. It's called UV 328, and it's a UV protection additive in transparent plastics. So this is also most likely going to be added to the Stockholm Convention of Persistent Organic Pollutants. So why the ugly? The ugly because they are actually known to be toxic in the environment and to humans. So they have a toxicological effect, and they're extremely persistent. You could argue that extremely persistent chemicals are also your artificial sweetener sucralose, but there are not known health effects or toxic effects with that chemical. That doesn't mean it's not doing anything, but we just don't know, and it's not interfering in ways we can track it in our body because it's so stable. It's going through our body, but we have incredible concentration. I just got some data from a stream in Anne Arundel County. We're talking about several hundred micrograms of sucralose in streams out there. So anyway, so these are the ugly ones. But I want to spend a little bit time, a few minutes, on the per and polyfluorinated substances. So they're called per and polyfluoroalkyl substances. This is actually used as a term. In short, PFAS. They are regulated now. Their regulation goes into place by EPA, by the Environmental Protection Agency, in drinking water now. So they're gonna regulate these substances in drinking water. They're persistent, they're extremely long-lived, and they make it through the water cycle and now ending up to concerning concentration in our drinking water, because we're also not great in completely removing them, because some of them are actually quite mobile in the water. So, but they're not new, interestingly enough. They've been actually manufactured since the 1940s. So they went under the radar for a long, long time. So they had time without even people looking at them too much to accumulate to a level where we're dealing with it now, and now really created a big, big problem with those. They're extremely stable. And as I mentioned, they're framed as forever chemicals. But the problem is that there are actually adverse health effects associated with them, which we know more and more about them. The regulation goes in place is only on a handful, but we know actually quite a lot of those. But PFAS are, in fact, some of them are even food additives, if you believe it or not. But they're in a lot of household products and end up in drinking water, as I mentioned. They're also in fire foams. So firefighters use them all the time. They have excellent firefighting properties, so they extinguish flames very well. The military have been using them all the time. And if you know the military, they always exercise. So they always have exercise for firefighting. And they have incredible levels now in some of our bases in the US of these chemicals. And they have a big, big problem at hand to clean this up. Why are they so stable? So now, little chemistry, the carbon-fluorine bond is actually the strongest chemical bond in organic chemistry now. So think about it when you try to make something. You can make these pretty easily, but you can't destroy them very easily. So that bond is amazingly stable. And think about that, the carbon-carbon bond in your alkane and so forth, in any kind of hydrocarbons is stable. This is not even comparable to that bond between the carbon and the fluorine. That makes them so problematic and so long-lived. Here's just a little bit of cycling. So because it's so long-lived, it really cycles. You can really call it a PFAS cycle, which means it is released through wastewater treatment plant, goes into the rivers, it's taken up by a drinking water plant, goes into your drinking water system, ends up in the wastewater again, and circles again. We have a lot of contamination sites where you have infiltrated the soils with these, and they slowly leach out. Landfills are a big problem now as well. There's leachate coming out of landfills, which is collected. PFAS concentration are through the roof there too. And that is typically treated to the extent that it can be actually discharged into a wastewater treatment plant. Well, you're just contributing to the PFAS cycle. So to break the cycle is a wicked problem. I'm going to deal with this for a long, long time in the future. All right. So coming to an end almost, but I wanted to mention a few things which also dissolve in water. And again, when we talk about drinking water and health, I think we need to mention also heavy metals. That's not necessarily the research I do. I more look at the organics, but for completeness, and I also call them the ugly because they're very toxic. So two metals I want to mention, which are always a problem, also in Southern Maryland, arsenic. You might want to test your well water actually, depending on which aquifer you're tapping into. Arsenic could be a problem. And of course, if you will go into the detail, arsenic has different species, and one of it is called arsenic 3. It's the most toxic one. When it comes from geological natural sources, actually, it's not necessarily from contaminated sites from anthropogenic sources. And here's a ratio. It actually it's often a natural contaminant. It's a ratio of 3:1 between natural and human. But it is extremely toxic. Some regions in the world have even greater problems than we have. Especially in India, Bangladesh, and other areas, they have huge problems to create safe drinking water because of arsenic. Lead, of course, we all remember Flint and what happened there. I want to give you a little bit of a background why that happened and why lead is a problem. You probably also seen the infrastructure proposal by the Biden administration to take out lead water pipes. And the reason for that is lead is actually they used to make lead water pipes. Lead itself, lead 2+, it's very toxic, especially in infants. It causes huge problems in the development of infants. And there's a lot of studies, especially out of the UK and Scotland. I worked actually on lead water pipes during my undergraduate study in the semester abroad in Glasgow. They have to go through a lot of treatment to minimize that lead from the pipes leaches into the water. And they're raising the pH, they're adding phosphate, they're adding carbonate, and so on, because they can't change the water source. They have water which is corrosive, which has what we call a low pH, so it actually would dissolve the lead pipes over time, and that means you're getting high concentration of lead. I think we should have learned from the Roman Empire, but apparently we did not, because they used lead linings in their aqueducts as well. So with that, I'm hoping we have some time now for some question and answers. I know this was just a broad overview with some work we do here, and of course, putting it in a larger context. So with that, just a little bit how we work in the lab. That's usually how my lab looks like.
Not true.
Lately, it's more like this. So for now, that's what I wanted to talk to you about today. And if you have questions, Tom will moderate it as I understand.
All right. Well, thank you, Michael. I will get to as many of the questions as I can, but I will remind you if we don't get to your questions, I'm sure Michael is happy to answer them and happy to receive contacts by email that you see on the screen. So the first question we received was fairly early on by someone who logged in with the username ESAT. And it was referring back to your initial forest of disinfection byproducts. And they ask, what concentrations of these chemicals produced at relative to a toxicology level?
That's a very good question. And it really, again, unfortunately, that answer is it depends and depends, depends. Depending on how much of carbon in general gets into a treatment plant, so that we call it dissolved organic carbon, we can measure it. And then also of this composition of this material. So the regulated compounds, they have a threshold, obviously, and the drinking water treatment plants are mandated to not go over the threshold. But again, there are only 12 compounds. So there are other compounds which we know they are toxic at that levels. They're found in some treatment plants, not all. That again, it depends on what is in the water. So it's not an easy answer at that constant, we're finding this concentration, that concentration. And it really is highly dependent on that treatment plant. But they are quite low. We're talking about probably ranges in the nanogram per liter ranges. We can measure quite a few, like about 800 of those are known on structural level, and they can be quantified, not in my lab, but other labs. Susan Richardson, if you want to Google her at the University in South Carolina, she does a lot of work. She worked for EPA, and she quantifies these disinfection byproducts on a regular basis, and they did tox tests on those concentrations they're finding, and they're finding that chronic toxicological effects exist at this level.
So lots of questions about the POPs. So the first one we'll deal with first, which is the UV238, which is added as a stabilizer for clear plastics. And Alyssa asks whether UV238 persists or leaches into water from goods that we use to potentially eat and drink from.
As far as I understand it, not necessarily UV protection in packaging material, but that's a very good question. I might need to get back to you on this, because I don't have the answer in terms of if it's a concern for food packaging. I believe it is not.
But if you were to buy a clear plastic drink bottle,
right?
For
it's
example.
not. It's in specific polymers as well. It's not in all. Let's say in a drinking water bottle like PET, phthalate, that's not where it is in. So it's not like a clear, all the clear plastic bottles you're buying and have that chemical in there. It's a specific additive for a specific purpose, clear plastic material. So not in the drinking water.
All right. From CJ Bright, who asks, does distillation remove PFASs and other persistent chemicals?
Yeah, when you distill water, and if you do it correctly, you're leaving most dissolved chemicals behind, including those organics. That works. Also, most PFAS can be removed by what we call reverse osmosis. These are membrane technologies. They're very expensive. That's why we're unfortunately not really implementing those to make drinking water on a large scale. Desalination plants work like this because they have to. So they use membrane technology, and the technology is around to remove them. But again, at most drinking water treatment plants, it's just too expensive for them to do so.
Jim Hurley asks a couple of questions. The first one was about PFASs on a Patuxent Naval Air Station, and I think you probably answered some of the questions on there, but he followed up with how good are refrigerator water filters and perhaps water filters in general in cleaning the water that we drink.
Mm-hmm. So they're based on what we call activated carbon, which is actually used in the drinking water treatment plant as well. So when they had the problem with the microsystems, that's what they did. They actually implemented another granulated activated carbon filter to get rid of it. So it's a good treatment to reduce further organics and metals as well. So they're binding to the activated carbon. So they are very useful in that regard. And they're likely to lower down dramatically also the chlorinated organics or the DBPs.
Just as interest for those who are on the Zoom meeting at the moment, if you go to our Science for Citizens website, we've recorded all of these, and one from a couple of years ago was from a former CBL student called Heather Stapleton, who actually did a comparison of different kinds of water filter and what they produced. So a gentleman called William H. puts you on the spot, and he says, what water do you primarily drink, and what do you do to it, if anything, before you drink it?
So I'm very sensitive to the chlorine taste, first of all. That means we actually have been experimenting with a lot of different fridge filters. So that question came up. So we do have one. Some actually produce a very strange taste, and others. So we probably now in the 6th or 7th brand, and the one we just found is pretty good for my taste. Anyway, so again, the activated carbon and the micro mesh systems, these have worked pretty well. There are ways, more sophisticated ways for homeowners to put in a system. So that's what I do. I drink that water. I never buy bottled water because I think it's the bottled water, by the way, that is not necessarily better, to be honest. In fact, I think if you run it through a fridge filter, that water is probably cleaner than your drinking water because it's differently regulated. So I'm not claiming you should drink bottled water because there's a lot of chemicals leaching out from the plastic. It's not necessarily that UV filter I described, but others. So another issue for another day.
We're staying on the same theme. Mariah Mackenzie asks, is there a way for citizens to test drinking water or local waterways for PFAS?
PFAS analysis are expensive, and even actually Maryland Department of Environment and MDE is out contracting at the moment samples. So I believe that's going to be a big challenge to do so right now. Although I'm hoping that that capability will improve in the future, because I think it is important that we do know what's in our water, especially if you have not very deeply drilled wells and you're maybe close to an installation where they might have used those firefighting foams.
So Jack Morton says, you described some of the uses of PFAS and other persistent pollutants in everyday use. Are they used because they're irreplaceable, or are they used because they are cheaper than other alternatives?
It's a bit of both. I mean, they have been used because of their incredible properties, right? So chemicals are manufactured for a specific purpose, and PFAS is no exception. They're incredible, interesting properties, chemical properties. That's why they were used for a lot of things, including, like I said, the firefighting foams. The problem is that we just gain knowledge about them after the fact they've been mass produced. So there is initiatives called green chemistry, it's been around for a while, to really replace problematic chemicals. And in fact, they've done a great job. They've phased out like phosgen, for example, as a major chemical for mass-produced chemicals in the past. That doesn't exist anymore. So the movement is certainly towards alternatives. And I think we're on a good trajectory there. However, we're dealing with things, like I said, PFAS is nothing new. They were produced since the 1940s, and they're continue to be produced more and more and more over the last 50 or plus years.
Lots of questions about filtering systems in the home, whether they're activated carbon or other systems. So would you say reverse osmosis would be the gold standard, that would remove most?
Yeah, it would. But keep in mind, these systems take a lot of power. You need a lot of pressure to do them. They are not maintenance free. In fact, quite the opposite. The membrane themselves are pretty expensive. So the question stands, what is more ecologically speaking better, to use a fridge filter, which is lasting for quite some time, or RO system? Reverse osmosis system are fantastic in that regard, to taking out the organics. It's not necessarily taking everything out, but it is just, it's a very advanced technology for that, and it is readily available, but it is expensive to run in a way. So yes, I guess I would call it a gold standard in a way, but I think for all purposes, like I described, the fridge filter will prove that pretty close.
Okay, so activated charcoal is good. Reverse osmosis is fantastic, but it's got upkeep costs and other. Okay. So you've raised lots of questions about chemicals that are released into the environment. And I think I'm interpreting this question correctly, and sorry if I mispronounce your first name. I think it is Saida Hussein. And Saida asked, how can this be prevented in the future. And I assume Saeed is talking about this issue of we're always chasing our tail, identifying chemicals that are in the environment, not effectively before they get into the environment.
Yeah, I mean, I think we to a specific extent, we have to live with it. And I think we can, because like I said, we don't even know the natural organic molecules floating around, what they are on a structural level. But we have been designed by evolution to deal with it. That doesn't mean we're creating new chemicals that we don't know what to do with it. But it does also not mean that everything is absolutely toxic. And that was not my impression when raised. I wanted to raise the issue that we're dealing with incredible diversity, incredible complexity of chemicals. And I truly believe that we are, as soon as we raise an issue and it really becomes a problem, supported by toxicological assessments, that the industry is not, I mean, but it's not our enemy at all, actually. In fact, they are really environmentally aware and they're really trying to create chemicals which are safe for the environment. So, however, we still have problems at hand which are long-term problems. This is not something we can easily solve. And that's why I call them the ugly, because they're going to be with us for decades to come. And unfortunately, there's not a sort of a bullet to solve the problem.
And last question. So Jack Morton asks about the water cycle, and you've emphasized the movement of water from precipitation through the ground into lakes and rivers and the ocean and back up to the atmosphere. So how much do water-soluble pollutants tend to spread versus staying local to the site of contamination?
So this has to do with the property, what we call, this is a technical term. So hydrophobic compounds are the ones that don't want to be in the water. So they're kind of things like your oil sheen, for example. And there are other chemicals that love to be in water because they're so soluble. So the solubility of a chemical is a chemical property, and that determines how mobile it is. If I take sucralose, which is not the fisher sweetener, it's designed to be extremely soluble because you want to taste it, you want to have it dissolve and everything. That is so mobile, it's not retained by anything. So that means if it goes into the wastewater, it comes out unchanged on the other end, and it will go its way for possibly decades to go. Whereas if you have a compound which is really hydrophobic, that means it doesn't want to be in the water, it sticks to the soil, it sticks to any particles in the water, and so on. So it's more likely to stay put where it was released. But unfortunately, with all those chemicals, we have the entire bandwidth of all those chemicals, which are extremely sticky and extremely soluble, and everything in between.
All right. Well, Michael, thank you very much for the presentation tonight. A reminder to all who are still on the Zoom call that you can see any of our previous Science for Citizens recordings. If you just search for Science for Citizens on Google and CBL, you will be taken to our page. Those of you who registered tonight and indicated you were happy for us to contact you will receive a link, a specific link to the recording of this presentation. And next week, we will be back for the penultimate of our spring Science for Citizens, and Dr. Solange Filoso will be talking about the efficacy and the impact of stream restoration in the Chesapeake watershed. So I invite you all to join us next week, Tuesday at 7 p.m. And I thank you all for your attention this evening. And Michael, thank you very much indeed.
Thank you.
For the clapping for the 100 people on the presentation. Thank you all.